A groundbreaking discovery has left scientists in awe. A satellite has captured the first ever detailed view of a massive tsunami, revealing secrets that challenge our understanding of these powerful natural phenomena. On July 29th, an earthquake of magnitude 8.8 struck the Kuril-Kamchatka subduction zone, triggering a tsunami that raced across the Pacific. While such events are typically monitored by DART buoys, this time, something extraordinary happened. The Surface Water and Ocean Topography (SWOT) satellite, a collaboration between NASA and CNES, happened to be in the right place at the right time. Designed to monitor Earth's surface water, SWOT captured a high-resolution image of the tsunami's wave field, offering an unprecedented perspective that has scientists rethinking their assumptions. Instead of a simple, unified wave, the satellite detected a complex, braided pattern extending for hundreds of miles. This level of detail, previously unattainable, has revealed that large tsunamis may behave in ways we never imagined. The findings, published in the Seismic Record, could revolutionize how scientists model tsunamis, issue warnings, and prepare coastal communities. But here's where it gets controversial. The satellite imagery showed the tsunami wave breaking apart and recombining mid-ocean, a clear sign of wave dispersion. For years, most tsunami models have treated large waves as non-dispersive, assuming the energy travels uniformly. However, SWOT's observations have exposed the limitations of these models. In this case, dispersion played a crucial role, with wave energy splitting and scattering, impacting the wave's behavior as it approached the coast. This extra variability could mean that the main wave is influenced by trailing waves as it nears certain coastlines, explains Angel Rizangulo, lead author of the study. We need to quantify this dispersive energy and assess its potential impact. This isn't just about refining models, it's about improving real-world risk assessments. If coastal warnings are based on oversimplified assumptions, they may fail to account for critical factors, especially in areas with complex shorelines or harbors. The SWOT pass also provided valuable insights into the earthquake's rupture mechanics. By combining SWOT data with DART buoy readings and seismic models, researchers revised the estimated rupture length, improving our understanding of the event. This data fusion approach, combining surface altimetry and deep ocean sensors, offers a powerful new tool for tsunami science. In the future, real-time integration of multiple data sources could enhance forecasts during live events, providing more accurate and timely warnings. It is crucial to mix as many data types as possible, says co-author Diego Melgar. The improved rupture model highlights how SWOT's measurements can bridge the gap between surface wave behavior and subsurface earthquake dynamics. The 2025 Kuril-Kamchatka tsunami was a unique opportunity, and SWOT's success has opened doors to a new era of tsunami forecasting. With growing concerns about coastal vulnerability and sea level rise, the need for faster, more accurate warnings is more critical than ever. If future satellite systems prioritize ocean surface mapping with real-time data delivery, they could be the key to more effective early warning systems. The bigger lesson is clear. Tsunami models must evolve to account for dispersion and the complex physics of wave behavior. So what do you think? Should we prioritize investing in advanced satellite systems for better tsunami warnings? Share your thoughts in the comments.